basically, without further ado, I would like to hand over to Luke Marsdon. But before I do, we're going to try an Icelandic thunderclap. So we're not going to do a round of applause for Luke. We're going to do an Icelandic thunderclap. So when we get to it, then let's do it then, because, yeah. So without further ado, may I hand you over to Luke Marsdon. Thank you, Luke.
Thank you very much, Nick. I think this is on. Oh, did you unlock your laptop, please? Oh, yes, sure.
So one note is that the keynote is going to vamp into the first session, and that's why we asked you to be in the right room for the 9:30 session. So Luke's session, we'll do a really quick turnaround, stay in your seats, and then we'll be on to the first session. So thank you very much.
Use this one. Test. Okay, cool. Hi, everyone. Welcome to Bristech, and thank you, Nick. I'm really excited to be keynoting such a lovely event. So I'm going to talk really quickly about the future of MLOps. And so I'm curious, who here, raise your hand if you have an inkling what MLOps is. Okay, so we'll get to that. But first I wanted to talk a little bit about sort of how we got to where we are today, sort of a state of the union for DevOps, software engineering, and machine learning. And so the spoiler really is that MLOps is the combination of these three disciplines. There is a real theme around Bristech at the intersection of DevOps, software engineering, and machine learning. And that was something that Nick communicated to me very clearly when he asked me to do the keynote, was that these themes really run through the whole event. And so I wanted to just take us on a whirlwind tour of how we got here. Software engineering, obviously, is how we write software. Who in the audience is a software developer? Okay, awesome. So you all know this. Obviously, we started out with punch cards and multi-user Unix systems back in the day, big mainframes. And then the rise of the personal computer came about, and then we connected those computers together with the internet. But at this point in history, we were still emailing patch files around to each other when we were doing software development. And that made it very difficult to integrate software, to collaborate on creating software products and software solutions. And then centralized version control happened, and tools like Subversion, which I'm sure many people here are familiar with, made it easier to keep track of and control the work that was being done, so that it was less of everyone maintaining their own copy of the source code and manually integrating patch files. And then in sort of the late 90s and the 2000s, distributed version control really took off, and tools like Git and GitHub are now absolutely essential to the way that we work as software engineers. The key point there is the ability to take someone else's work and fork it, make a copy of it that you can work on in your own controlled environment without treading on their toes, and then propose changes back to them, and have all of that process of developing software being tracked and collaborative and distributed. So that's how we write software in a nutshell. DevOps, of course, is how we deploy software and how we deploy and monitor it. So when we're actually putting applications live. And so back in the day, we used to edit code live on the server, or at least I did. I'm guilty of that. And then we also used to build binaries for compiled software, and sometimes in big companies, binaries would get emailed around. So you'd email the binary or the WAR file or whatever to the ops team, and you'd sort of throw it over the wall, and you'd say, okay, now run this, now operate it. And of course that was problematic because it meant that there were silos, and different teams were disconnected from each other, and the people who wrote the software didn't have to operate it, and that meant that there were often long cycles, big outages, and huge challenges when trying to operate and scale a software application in production. So then continuous integration happened, and tools like Jenkins and GitLab became very popular, and this dramatically improved the state of software operations, the ability to deploy an asset that was built in a central place, that came from a sort of trusted record of how that asset was created and how it was deployed to production. The other thing that happened around DevOps, of course, was this big social change and this big cultural change inside businesses to go from having a separate software development team and an operations team to unifying those teams. And of course, that's the movement that's called DevOps. It's development and operations together. And of course, the public cloud also happened. So we moved from running our applications in our own data centers, and I used to run a web hosting company, so when the server needed upgrading, you went to the physical data center and you upgraded the RAM, you pull it out the rack and you unplug it and you plug it back in again. There is currently a mass migration away from running your own infrastructure towards using cloud infrastructure, where increasingly sophisticated services are available just behind an API call on AWS and Google and Azure and so on. And there's also been a huge move towards immutable infrastructure. So even when continuous integration is used to build an application, if that asset is then manually copied into an environment where it's running in production, then that leads to all sorts of chaos and pain around, like, who put that version live, and there isn't a record of where the version that's running in production came from. And similarly with public cloud, it's possible to have a CI system create AWS images, for example, and deploy an entire set of microservices as individual VM images. Now, that's problematic because VMs are quite heavy, and so spinning up and down whole VMs when you upgrade your software, well, it's kind of 2005. And so there's been this additional sort of layer of abstraction that's come up, which is called immutable infrastructure. And this whole world of Docker and containers and Kubernetes is all about being able to have a layer of infrastructure which is sort of fluid. It's like a human body in the sense that all of your cells get regenerated, and in 5 years, you're actually not the same matter that you were before. This happens with immutable infrastructure, where you can add machines to a pool of compute, and you can take other machines away. And the whole notion here is sort of cattle, not pets. So immutable infrastructure has been enabled by containerization, the ability to package up applications in Docker containers and then deploy them across a cluster with Kubernetes. And then tying this back to the versioning theme in the software development piece, there's this notion called GitOps, which is that you should record the version of everything that's running in production in a Git repo, and that the source of truth for what's running in production should also be version controlled. So it's kind of like version control for operations. So this is sort of the state of the art, as far as I can tell now, with DevOps. The other thing that's happening that's really interesting is that machine learning is suddenly becoming very popular. So I can give a very brief sort of background to machine learning. I mean, machine learning is how we use data plus maths to train models to make decisions automatically. And this is actually, it's really interesting because it's a new type of software in a sense. It's software that's driven by data rather than software that's just created manually as code. And so back in the 1700s, there was lots of mathematicians doing maths on on paper and on blackboards. And that's where the sort of fundamentals for machine learning came from, these ideas of being able to fit curves, to closely match data points in many dimensions. And that's how linear regressions work, which is a simple form of machine learning. Then in the, I think it was the 1950s, the first application of things like Markov chains. Markov chains were invented, which is the ability to predict what will come next in a sentence, for example, and you can create all sorts of fun gibberish poetry by using Markov chains. And there was an invention called the perceptron, which was the very first neural network, which is trying to simulate the action of the human brain in a computer. Also happened in the 50s. And then something really interesting happened in the 60s, is that there was what's called the first AI winter. I call it the first because there may or may not be another one. But what happened in the AI winter was that there was a lot of hype around AI. There was a lot of hype around artificial intelligence and machine learning. But the problem was that the computational power was not there to actually do it at scale. And the computers in the 60s were not powerful enough to really simulate a human mind. But then in the 70s and the 80s and the 90s, there was the rediscovery of backpropagation, which is the technique that's used to train a neural network. And if you're wondering, by the way, this image here is a map of a real neural network, courtesy of GraphCore, one of the big Bristol tech giants. They make these nice pictures of neural networks. And so into the 2000s and the 2010s, deep learning finally became computationally feasible, which is where you can use huge data sets to train artificial minds to be able to do things like recognize pictures of hot dogs and cats and other valuable things. And so the point I'm trying to make with this talk is that as machine learning is really now finally, with the computational power available to it, and the change in the industry to recognize it as actually a meaningful force for good, machine learning is emerging from the world of research and academia. And now we have to get serious about, well, how do we operationalize machine learning? And the whole, the convergence of software engineering, DevOps, and machine learning is going to be called MLOps. That seems to be the emerging industry term that's used to describe this. And so I'll talk a little bit about MLOps and what you need to do in order to have a sensible approach to applying machine learning and deploying machine learning models and so on. And it's interesting because it's a bit more complicated than just regular software engineering. But first I just want to say that actually I believe that AI and machine learning has the potential to reinvent the global economy in quite a good way. I believe that it can reduce the number of menial jobs that people do, and I think that's a positive thing if we can find the right sort of economic model to make that work for people, although that's a whole other conversation. But as a discipline, sort of artificial intelligence and machine learning is really immature. Like I said, it's just started to become computationally feasible to do deep learning on large data sets. And therefore, it's really the Wild West. Everyone who's doing machine learning is doing it in a slightly different way. And a lot of people have sort of manual approaches to keeping track of things. And so we've done lots of surveys of companies that are trying to do machine learning, and we've seen really quite damaging levels of chaos and pain. Not in the stage where you're playing around with AI, that's actually quite easy. But when you go from playing around with creating models to actually trying to run them in production, and I'll talk a little bit about the problems that we've seen there. The first one is that lots of teams end up wasting huge amounts of time. And one of the main reasons for that is that they are inefficiently collaborating with each other. The tooling that I described in software engineering for collaboration between software engineers, where you can fork someone else's code and make a writable copy that you can work on and then contribute, propose a change back and merge from master if there have been intermediate changes. That tooling just doesn't exist for notebooks and data sets and the kind of metrics and hyperparameters that you have to deal with when you're doing machine learning. There's also the problem of manual tracking. Many places we've looked at, many companies we've spoken to, they use like a shared spreadsheet to keep track of the models that they've created and where they came from and what version of the code they used to create those models and what data set they trained the models on and what version of the data set, if you're lucky. And yet these spreadsheets are an anti-pattern. I mean, imagine if you had a spreadsheet for your builds in your CI system and for continuous delivery. It would be pretty chaotic because you'd be relying on humans to track things correctly and not make mistakes. And that leads into this other problem of not being able to reproduce your work. And so the whole world of immutable infrastructure and Docker containers and Kubernetes for software engineering is wonderful because once you've got a Docker container, you can run exactly the same Docker container. You can scale it across multiple machines, and you know exactly where it came from because it's tagged normally with the SHA-1 hash of the Git repo where it came from. And so you can reproduce that. But with machine learning, you've got lots more moving parts, and so reproducibility is harder, and provenance, which is knowing where something came from, is harder. Another problem that we've seen in a lot of companies is that companies are struggling to deploy their models at all. And that's often because of a sort of cultural mismatch between machine learning engineers or data scientists who come in with a maths background and aren't familiar with the world of Docker and Kubernetes and DevOps. And so they're just doing stuff on their laptop, and Python is just a tool for them. But there's definitely a gap, and there's a sort of a new silo is forming between machine learning and DevOps, which is a problem. Another problem is that people deploy models into production and then they don't know what they're doing. As in they don't know what the models are doing once they're running in production. That's problematic because, you need to keep an eye on your models. You need to know what they're doing. But models are not like regular microservices because they can be reporting completely normal latencies and error rates, and actually they've gone haywire and they're making crazy decisions that are completely wrong. And so you need new tools to introspect the behavior of these models. And the funny thing is that we've kind of been here before. So back in the 90s, like I described in the introduction, the software engineering was siloed. Not all source code was version controlled. Often people would email tarbles or patch files around and maintain local copies of source trees. There was certainly no continuous delivery, let alone continuous integration and automated testing. And in that context, software took months to ship, and when there were problems with software, with a release that might take several months to ship, it would take weeks or even months to fix problems with it. And now software is shipped and iterated on in minutes. And so I believe the same is possible for AI by solving what we call the MLOps Manifesto. And so if the following 4 things can be true of a system that you create to do artificial intelligence and machine learning, sort of DevOps for ML, if you will, then you're going to have a much better time and everything is going to be a lot smoother and less chaotic. So the first one is that your models have to be reproducible. You have to be able to retrain a model that another colleague created 9 months ago, and you have to be able to retrain it on the same data with the same version of TensorFlow or whatever libraries you're using, and you have to be able to get the same model accuracy to within a reasonable percent of model accuracy. Models also need to be accountable. That means that accountability in the same sense that we hold humans accountable for their decisions. So if you have a judge making decisions in a court, then you at least need to know who that judge is and on what basis they're making their decisions. And the equivalent for machine learning is that you need to know what the model is and where it came from, and on what basis it's making its decisions is what data was it trained on. And this is a basic sort of fundamental requirement, that without having accountability of models, then you're going to end up in this very chaotic situation where people are just flinging models into production and they have no idea where they came from, and they're not able to reproduce issues with them and fix them later. The next one is that the model development has to be collaborative, and that means that we need tools that allow the same possibility of taking a, if I'm working on a model, for example, then I need to be able to have someone else come and make a copy of my working environment, including all the data and including the history of different metrics and hyperparameters, different hyperparameters that I've tried and different metrics, like accuracy score that I might have achieved. And then I need to be able to propose those changes back to the upstream in exactly the way that Git flow has enabled that to be done for software engineering. And then finally, once models are deployed into production, you need to be able to deploy them continuously, so automatic deployment, not manual SCPing files around. And then once models are running in production, they need to be monitored statistically. And so I mentioned just now that monitoring models is harder than monitoring regular microservices because they have this sort of behavioral aspect that you need to get your hooks into. And the reason for that is that if you already knew, if you imagine a road signs model, so for example, you've got an autonomous vehicle that's driving around and it's got sensors, it's got cameras, and the cameras are looking at different road signs, and they're trying to classify those road signs. If you've got a fleet of autonomous vehicles driving around classifying road signs, how do you monitor that fleet? How do you know whether they're getting the road signs right? Well, if you already knew the answer to what road sign is in this image, then you wouldn't need the model. So, like, how do you keep track of these things? And this is an interesting puzzle, but there are some statistical techniques you can use to get insight into the behavior of these models that are running in production. And so, for example, if the number of stop signs that your autonomous vehicle fleet suddenly drops from the normal level, say maybe 10%, if it drops down to 0, then there's definitely something fishy going on, and it would be really good if you could alert a human to that as soon as possible so that they can dip into the stream of data and see what's actually going on. Because it might be that someone deployed a bad model, in which case you definitely want to know about that because you want to roll back the model. Or it might be that there's something weird about the model, or it might be that something changed about the world. Because the way that these models recognize things often don't correspond to what you might expect. And we've seen stranger things in machine learning than models not being able to recognize road signs in the snow, for example. So maybe it snowed, and now your model stopped working, in which case you definitely want to know about that as well. So I'm just very quickly going to point out that data engineering and machine learning as a life cycle is different to software development in an interesting and important way. The point is here that at the top, there's software development, which is basically a code, test, deploy, monitor cycle. But with machine learning, you've got lots more complexity because you've got data and you've got models and all of the combination of these things. And so the key point here is that you have to track runs, not just versions of code. So you have to track the relationship between a version of the version of the code that was run to either do some data transformation or a model training, and the resulting artifact, the model, for example, or the intermediate data set. And so this notion of tracking runs turns out to be crucially important to MLOps. So I'm out of time, so I'm going to skip over these pieces. But I'll be all day in WS2, the room with the booths, and if you'd like to come and talk about MLOps, please do. If you're interested in these topics and you'd like to get in touch, please drop me an email. I'd love to chat. Yeah, come and see a demo of MLOps.
Hold the applause. Basically, what I'd like to try here is the old Icelandic thunderclap. So
What
I don't know
is the Icelandic thunderclap?
You're about to find out, Luke. so I don't know if guys and gals have ever done this, but we can do one single clap, which is after 3. We're just going to raise our hands to do a clap. So ready? 1, 2, 3. Beautiful. Okay. So Luke's going to be around for the rest of the day. If you have questions, awesome. We are going to crack on in each individual room now, swap it over, and we're going to carry on here in Cinema 1. So thank you very much.